Hello everyone, we're starting Chapter 6 today, and Chapter 6 is really just a continuation of the Chapter 5 material with force and summation of force. But we're going to continue by adding to the list of different forces that need to be considered for different systems of motion. So far we have our gravity force, which will just equal mg as long as we're on the surface of the Earth, and gravity always has to point down. We have the normal force, which always points normal to the surface of contact, and this means that the mass physically has to be in contact with some other surface. And then we also had a tension force, and this was where if we attached a rope or a chain or some other support structure, then that rope would provide a tension force that pulls away from the body, because a rope cannot push. That's not the way it works. And we saw multiple examples using these three forces to move objects around, and then we started incorporating multiple masses connected by ropes. We put those on inclined planes, and we saw how to set up the sum of forces for those systems, keeping in mind that every mass deserves its own sum of force expressions, and that means that every mass in the problem can have its own reference frame, and that was critical to helping us solve some of those larger systems of forces, especially the ones that had different inclined planes. But in Chapter 6, we're going to move on to two different types of force. The first one we're going to look at is the friction force, and obviously this will be the force that results from the interaction of friction between two surfaces. And then we're going to look at centripetal forces, plural. And as I mentioned in a previous video, centripetal force is not going to be something new that we have to define. Instead, it's going to be the result of one or more of these forces that are causing circular motion. So one of these forces points towards the center of a circular path, and that force is what is causing that circular path to be followed by the mass that is at that particular radius. But we're gonna wait until we've completed our discussion on friction, because we're going to see how friction can be used as a centripetal force. So this will probably be the last video for Chapter 6, is the centripetal forces. But for friction is probably going to take up 2 videos. The first one pretty much just to define friction and explain why it's happening and how friction causes objects to slow down. The second video for friction will look at a number of different example problems, and then we should really only need about 3 videos for this chapter. The third chapter we can look at different combinations of all of these forces as they apply to centripetal systems. So for friction, we'll start with a fairly straightforward example. We have a mass that's sitting on a flat horizontal surface, and this surface is kind of rough, and so there will be friction. All the other case scenarios that we've had before this, we've always considered no friction in the system. Likewise, no air resistance. We're going to continue with the idea that there's no air resistance. Air resistance is a very complex mathematical hurdle, which is better suited for a classical mechanics course. But we can take care of the friction discussion pretty easy. So what I'm going to do is apply some kind of outside force so that we can get this mass moving. But then if we zoom in and take a closer look at the interaction between the surface of this block and the tabletop, and I mean really zoom in, like with an electron microscope. And if you've ever seen images of electron microscopes, objects that look flat, to us in the microscope, they look like mountain ranges, because that electron microscope is going to be able to differentiate between almost individual molecules. It's not quite that good, but it can really differentiate between the different layers of the material. And no matter how much we try to smooth out a surface, there's always going to be these little peaks and pits on that surface. So what I've just drawn here, this mountain range here, this is the tabletop as viewed under a electron microscope. And then the surface of the block, well, even the block surface, if it appears smooth to us under an electron microscope, it's probably going to look like another mountain range, except this one is inverted. It's upside down. And so you have these two surfaces that are pressing against one another. And as that happens, we have the weight of the block, which is pushing down on the tabletop, and we have a normal force from the tabletop pushing back up on the mass. And this is stuff that we already know from our Chapter 5 discussions. But now we have this applied force that we're going to use to try and drag our mass across the tabletop. Now imagine what would happen down here if you were to try to drag these two surfaces across one another. Because the surfaces are so jagged, you would end up basically getting hung up on all of these different peaks. As the block slides across the surface of the tabletop, we keep snagging between the peaks. And so every one of those snags causes some kind of equal and opposite force interaction. And what we need to do is we need to figure out, how is that going to affect the motion of this block? And this interaction of force counterforce is what we refer to as friction. Now, if the applied force is small enough, then the block is not going to move. If you can imagine that this is a very, very heavy box that's sitting on the floor, and you're trying to push that box across the floor, you can apply some force to that box, but that's no guarantee that the box is going to start moving. And so that means you might have to apply a little more force, and maybe the box still doesn't start moving. And so you really start putting some effort in there. You're pushing really, really, really hard. You're applying a lot of force, and then finally that box moves. There's kind of a jerk motion, and all of a sudden the box starts moving and it starts sliding across the floor. So let's take that scenario and apply it to a graph. On the horizontal axes, we're going to have the amount of applied force that we have been placing on our mass. And then we're going to have what we call a friction force. And if we're applying our applied force to the right, so we'll let to the right be the positive direction. If we have our force applied to the right, yet the box is not moving, then that implies that there is some counterforce that is acting against the applied force, which is keeping the block from moving. And we're going to call that counterforce friction. So our friction force is going to be pointing in a direction opposite of whatever the implied direction of motion is. Our applied force is attempting to move the block to the right. As such, the friction force has to oppose that by pointing to the left. And that's going to be the first concept that we have for friction, is that friction will always oppose the direction of motion, or the implied direction. So what do I mean by implied direction? Well, right here, the implication is that as I apply a force to the right, the block should start moving to the right. But friction is going to oppose that motion by pointing to the left. And as we all know, there have been those times where we've tried to push something that's very heavy and it just won't budge. And that's because there is a counterforce that we are now calling friction that is preventing us from getting that large object to move. So now that we kind of have that understanding of the force counterforce situation, we'd like to graph it. So we have our applied force and we have the friction force. And if our object is to remain stationary, then the applied force versus the friction force, that combination is always going to have to add up to equal 0. Now I have that plus sign there, and you might be thinking, well, why is he adding it? The friction force is in the other direction. And that is correct. We can show that minus sign by rewriting these forces with respect to the positive direction in the system. The applied force is in the positive direction, so we would have positive F. But when I add the friction force, that's where I would add the directional aspect. And you'll notice now that I don't have the vector hats anymore. And so this tells me that at any time the applied force has to be equal and opposite to the friction force if there is no motion, if there is no acceleration. Well, that makes for a pretty straightforward graph. If I continuously increase the applied force more and more and more, and the block doesn't move, then that means that I have to have an equal and opposite friction force to go with it. So every time I apply a little bit of friction force, anytime I apply a little bit of force, I have to have an equal and opposite friction force. And if I apply some more force, I have to get more friction force. And what we end up seeing is a one-to-one relationship between the applied force and the friction force. I can continue applying more and more force, but if the mass doesn't budge, if the mass doesn't move, then that summation has to remain equal to 0. And this is important in helping us figure out what is the magnitude of that friction force. Well, it's pretty easy now. It's equal to the applied force. But then there's going to come a point where we have applied so much force that the friction force that's holding our mass immobile can't take it anymore. There eventually comes a point where all of these peaks that are snagging on one another, they can't maintain that equal and opposite pushing match, and one of these peak-to-peak interactions, in fact, probably more than one, is going to fail. And we're going to start seeing the block start moving across the tabletop. So that's that jerk motion that I mentioned before. And when that happens on our graph, we're going to see that sort of jerk motion, and then it doesn't matter how much more applied force we try to give that block. The block is now in motion. And all of these peak-to-peak interactions, they're still snagging as the block slides across the tabletop, but we've already got so much applied force that those snags are still not going to be able to keep the block stationary. As long as we keep applying that outside force, the block will continue to slide across the tabletop. And so this graph that we've just produced here shows us that there are two distinct types of friction. There's the friction on the left side of the squiggly line that I've drawn, where our friction force is equal and opposite to our applied force, and there is no motion, there is no acceleration. And if you're not moving, then technically you are static. Static refers to no motion. And so we apply this term of static to the friction, and we say that on this side of the graph is where we have our static friction. So this is a friction that keeps our mass from moving. It's a friction that keeps the mass static. So there should be no acceleration when we are utilizing a static friction force. But then there comes a point where we've applied so much force that we overcome the static friction and we start moving. And once that happens, the combination of the applied force and the friction force is no longer equal to 0. it cannot equal 0 if we start to move. And that's because we've gone from a static state to a moving state. And the only way you can do that is if you change your velocity, so there has to be some kind of acceleration involved, which means we could take the difference in our forces and set it equal to ma. But keep in mind, the whole point of the chapter 5 material with finding the sum of forces was to find the acceleration so that you could take that information, oops, spelled that wrong, and apply it to the kinematic equations of motion. So when this happens, when we overcome the static friction, we enter what is known as the kinetic friction case. So kinetic is just kind of a shorthand for kinematic. But this is the friction that we encounter as we are moving. Remember, just because we're moving doesn't mean that we don't still have all of these peak-to-peak snags. Those are still happening. But they're not, but the snagging effect is not enough to slow us down and keep us from moving. And the really interesting thing is over here in the kinetic side of things, we see that the line on the graph becomes constant. It basically flatlines. And so what this tells us is that there is a constant value for the kinetic friction. And we're going to label each of these respectively F sub k for kinetic friction and F sub s for static friction. So we've got kinetic friction over here on the right half of the graph. So what about all of this over here? Well, that's going to be the static friction. And now we can put some more detail to these equations over here. We have the one-to-one relationship between our applied force and our static friction force. And so what that tells us is that for any case scenario where we're applying force and our object isn't moving, then the static friction force is going to have to be equal and opposite, or we could say equal in magnitude to the applied force. Until we get right up here where we basically break the static friction. We have that jerking motion, and then we end up with the kinetic friction case. And the kinetic friction, well, that's a constant, and that's somewhat beneficial to us, because at least if it's a constant, then it makes the math easier, but we need to figure out some kind of a mathematical expression that tells us what that constant value is. At least for the static friction, you know, we can go through a sum of forces and we can find out just how much static friction we need to counter that applied force until we get up to the very top, until we get up to this breaking point here. And right here is where we are going to achieve what we call the maximum static friction. So this is the absolute largest amount of static friction that the system can provide before we go through that jerking motion and then we start moving. So with friction, it's either one or the other. you're either static or you're moving. But depending on which case you're dealing with, that tells you which of the two types of friction you have to work with. You either have to work with static friction or you have to work with kinetic friction. Okay, well we have our equation for static friction right down here. But what about that maximum static friction? Does that mean that it's going to equal the maximum applied force? Well, no, because we can continue applying more and more force to the system, but obviously we're gonna reach that breaking point. We're going to switch over to kinetic friction, but our applied force can still work even in a kinetic case. So this is not going to be how we figure out what the maximum static friction is. We could go through some kind of testing process where we keep applying more and more force to our mass until it eventually does start to move. And that's, that seems like a valid way of doing things, except it's not very practical, especially if, let's say, you're going to build a house on a hillside, and you want to know, well, how much friction is holding the house against the hillside, and what's the maximum amount of static friction that keeps the house from sliding down the hill. Well, in that case, you probably don't want to be running some kind of experiment to see how much it takes to get the house to slide down the hill, because then you're going to destroy the house. Instead, we'd rather have some other approach to measuring these systems. Now we can still do those experiments to see what the essential breaking point is for our static friction. So we want to continuously increase the amount of applied force until we reach that maximum static friction. And it turns out that there is a ratio that exists between our maximum static friction force and the normal force. Back in Chapter 5, I kept reminding you to go through your sum of forces and take the time to solve for the normal force, because eventually we're going to need to know what that normal force is. And today is the day. If we look at the surface-to-surface interaction between this mass and the tabletop, well, I've got the weight of the mass pressing down on the tabletop, and so the tabletop is pushing back on the mass. Well, what would happen if I placed another mass on top of the first one? Well, that would increase the amount of weight that is pressing down on the tabletop, and so the tabletop would have to respond by pushing back with more normal force. But effectively what you're doing is you're pressing this block down onto the tabletop, and you're forcing these peaks closer together as a result. And if you force those surfaces closer together, you're going to increase the amount of interactions that you get between the peaks. And you're going to get more snagging as those objects try to slide across one another. Well, so that idea of having a maximum static friction force compared to the normal force, the amount of normal force that we have. Well, why are we using the normal force? Why don't we use the weight? Well, because the weight of our object is based on the mass of that object, but the normal force would depend on how much total mass is present in the system pressing down on the tabletop. So we would have both weights pressing down on the table that would contribute to the normal force. But we'll just stick with the one mass for right now. So what we do here is we measure the ratio of that maximum static friction force. So that's the static friction force at that breaking point before we start moving. And we compare that to the normal force for the system. And the ratio of the two is what we call the coefficient of friction. And specifically, this is going to be the static coefficient, because remember, we have two different kinds of friction up here. We have static friction and we have kinetic friction. Well, so I guess that implies that there's a kinetic coefficient as well. This is our static coefficient of friction. We will also have a kinetic coefficient of friction. But what is that going to be defined by? Okay, here's where everything's going to start coming together for us. I'm going to think of, let's switch to purple for this part. Now, we already know that while we're in this static region of the graph, that our static friction has to equal the applied force. Okay, our static friction is there to keep us immobile. Our static friction will never be any larger or any smaller than the applied force. And what I like to do to kind of clarify that point is to say that static friction only uses what it needs. No more, no less. And so our static friction is equal to the applied force until we get to the maximum static friction. In this case, the maximum static friction is a fixed value for that system, and that's why we can measure it using this particular ratio. Likewise, the kinetic friction force right here, not only is it constant, but it's a fixed value for the system. As such, we can measure that as a ratio of friction force to normal force, and that is what's going to provide us with the kinetic friction coefficient. Okay, time to put this stuff together. So we have our static friction force, which, as we said, static friction is going to equal the applied force, because static friction only uses what it needs, but we have a means in which we can solve for the maximum static friction. All we have to do is look up this coefficient in a table somewhere, because this coefficient is measuring the surface-to-surface interaction that is happening between the mass and the tabletop. Each surface-to-surface interaction is going to be unique. If we were to take this this picture that we had here with the peaks and valleys, maybe that's a textbook sliding over a tabletop. And so the smoothness of those surfaces is going to tell us just how those peak-to-peak snags are going to play out in terms of the friction. But what if we switched one of these? Maybe if we switched out the textbook for a really smooth block of ice, and we put that on the tabletop. So it's the same tabletop, but that block of ice is probably going to slide way easier than the textbook did. And that's because there's a difference between the surface-to-surface interactions. But that surface-to-surface interaction can now be measured using those coefficients. These coefficients are literally telling us what the ratio of required friction force is to the amount of force that those two surfaces are pressing against one another with. That's what the normal force is. So every surface-to-surface interaction that you can possibly imagine will have its own unique coefficients. And so there are literally volumes and volumes of friction coefficients for different surface-to-surface interactions. As you're driving down the road, your tires have a certain surface texture that is associated with them. So you're driving down the road in your car, and your tire, if we zoom in on this here, your tire has a certain surface texture associated with it, which is going to that surface texture of the tire is going to interact with the surface texture of the road. Well, for the sake of argument, let's just say that your tires remain unchanged, but when it comes to the road, you could go from a concrete surface to an asphalt surface to a gravel road to a dirt road to an icy road. There are all different kinds of conditions to the road that can change the surface-to-surface interaction between the two. And the interaction between the two can be measured using those coefficients. And so on a nice spring day, when the road's dry and clear, you have a fairly high static coefficient between your tires and the road that keep your tires from slipping, and they keep you from losing control as you're driving down the road. But then winter comes along and you start getting snow and ice on the road. You start to see that static coefficient plummet. And now, because the static coefficient drops, your maximum static friction value drops as well. And so the tires no longer have the same grip that they did in the springtime. And so that it's far more likely that you could end up losing control as you're driving your vehicle, given those poor driving conditions. Well, then you can start considering the conditions of your tires. Are they brand new? Are they worn out and bald? Are they all-weather tires? Do they have studs on them or chains on them? All of those things can change the coefficient of friction. And so for our purposes, we will either already have the coefficients provided to us in our problems, or we'll have a problem specifically set up for us to measure the coefficient in that system. We will not have any of those situations where you actually have to go and look up in one of those numerous volumes the specific surface-to-surface interaction. But those things are out there, just so you know. You may end up in a situation in the future where you need to figure out, what might be the breaking point in terms of the static friction, like, when you build a house on a hillside. Is there enough friction to basically hold the foundation in place? And you would actually probably bury the foundation in the ground to give it a little more grip, but all these things start to come together in engineering problems, and if you don't pay well enough attention to things like this, you could end up building something that all of a sudden just slides down the hill, and now you've got a liability issue on your hands. So we have the distinction between static friction, which only uses what it needs until we get to the maximum static friction. Then we have an equation that we can use that will tell us what that breaking point will be. And then we have an equation which is very similar that tells us what the kinetic friction force is going to be. And the way these equations are laid out, they kind of spell fun. We've got F, we've got mu that looks like U, and we've got N. So if you can remember that friction is fun, then you can remember the equation. Even though friction just ends up making more math for us, I don't know that it's really that fun. But we would not have the life and the existence that we have today without friction. Because if we didn't have friction, things would just be bouncing around all over the place. Nothing would ever sit still, and we would never accomplish anything. All right, so we have our equations for our different friction forces, and we now see why the friction forces are going to act the way they do. Now would be a good time to apply all of this to a fairly straightforward example problem. So we have a block sitting on a flat horizontal surface, and someone has been nice enough to measure the coefficients of friction. We have a kinetic coefficient, which is equal to 0.5, and we have a static coefficient, which is equal to 0.75. Now you'll notice I did not put any units there, and that's because our definition for these coefficients is the ratio of two different forces. We have a friction force versus a normal force. Forces have the same units, and so our coefficients are going to be unitless expressions. They do have a number associated with them, but they're unitless. And the kinetic coefficient has to be smaller than the static coefficient. Now, why is that the case? Let's look back up here at the graph, and let's clean this up a little bit so that we can see things better. All right, so we start off with we're going to start off at zero applied force. So this was our applied force down on the horizontal axes. So we start off with 0 applied force, which means we have 0 static friction. And then we slowly increase our applied force until we get up to that maximum static friction. Then we reach that breaking point and we drop down to our kinetic friction. So if our equations say that static friction and kinetic friction can be measured using these two ratios, well, there's a lot of instances where the static friction was actually less than the kinetic friction force. So how are we justified in saying that the static coefficient has to be bigger than the kinetic coefficient? Well, that static coefficient is only used with respect to the maximum static friction. And by looking at this graph, keep in mind that if you want to get your object in motion, if you want to start moving an object, you first have to overcome all of the static friction, including the maximum static friction. Then you hit that breaking point and you drop down to a lower friction value for your kinetic friction. Now, I bring this up because in a previous edition of the book, there was a table of coefficients, and they listed out static and kinetic coefficients for a number of different surface-to-surface interactions, and there was one pairing where they had like 0.003, 0.003. The book had them equal to each other. Well, you can't have that. What happened in this case was that the editor in the book cut off the values too soon. There should have been like some additional decimal places back here to indicate the difference between the two. Okay, you cannot have a kinetic coefficient that is equal to the static coefficient, because then that means that you've got both case scenarios happening at the same time. You can't have something that is both static and kinetic. You're either static or you're moving. There is no in between. All right, so, but we've got two different coefficients of friction here. Obviously, our kinetic is smaller than our static, which is what we want. And so what we're going to do is give this block some mass. We'll say 5 kilograms. And then we want to apply some force to it. And I will apply a force of, let's say, 20 newtons. And all I want to know is, will this block start to move? So we do, whoops, what happened here? So we do have friction between the surface of the block and the tabletop here. But in figuring out if this block is going to move or not, we need to figure out if the amount of applied force is enough to overcome that breaking point with the maximum static friction. So essentially, we have to test the system. We have to test and see if there's enough maximum static friction to keep this block immobile, or if the applied force is too much, then the block will start moving. But once the block starts moving, then we have to switch over to the kinetic friction case. So one step at a time, let's finish the picture and figure out what all the other forces in the system are going to be. So obviously we're going to have the weight of the block that pushes down into the tabletop, so the tabletop has to push back with a normal force. Our applied force is to the right. I'm going to put in a reference frame here real quick. And so the implied direction of motion for this block is to have it move to the right, because that's the direction our applied force is pointing. We know that friction has to oppose the direction of motion. So we're going to have a friction force pointing to the left. Now, is that going to be kinetic friction or static friction? We don't know yet. That's why we're going to apply this test. Now that our picture's done, we have our reference frame. Let's put everything into a sum of forces. So in the x direction for sum of forces, we have our applied force to the right, that is F. We have our friction force to the left. Again, I don't know which friction force that is. And until I know for sure, the only thing that I can really say is that these two forces are going to get together and they're going to determine what the acceleration of this mass is. If the block remains stationary, then the acceleration will equal 0. If the block starts to move, then there will be some non-zero acceleration associated with this expression. But again, we have to wait until we've determined which of the friction forces we're dealing with. In the y direction, we have the normal force pointing up. We have the weight pointing down. The block should not lose contact with the tabletop, and there's nothing else in the system to indicate that the block will be pressed down or pulled up away from the countertop. It's just the normal force and the weight, and so those two should add up to 0. Now comes the test. We want to take this equation right here, and we want to test the friction force. We want to test and see if there's enough static friction force to keep this block immobile. And if we're going to test that static friction force, we might as well just go all in and test the whole thing. That means we need to know what the maximum static friction force is going to be. So back up here. Well, friction is fun. Our maximum static friction force is going to equal the static coefficient times the normal force. Now, we have our static coefficient right up here. It's 0.07. But we also have our normal force. That's why we've been getting in all the practice of solving for, it should have been the y direction, of solving for our normal force. In this case, it's just equal to the weight. So that means our static friction maximum value is mu s mg. You can plug all of our numbers in now. 0.75 for the static coefficient. We've got 5 for the mass. We've got 9.8 for gravity. Plug it all in. Gotta get my calculator app. Yep, couldn't find my calculator app. There it is. 0.75 times 5 times 9.8 is 36.78, so I'll just go 36.8 newtons. Okay. So this is the absolute highest amount of static friction that the system can provide. And so now what we do for our test is everything over here, as we said, is going to tell us what happens in terms of the acceleration of our mass. Well, the summation of these forces can have one of three possible outcomes. At this point, I'm not so interested in what the actual numerical outcome is. I want to know, is this combination a positive outcome? Is it a negative outcome? Or maybe, just maybe, it's a perfect balance and we get 0. Well, what does it mean for this combination to be positive? Well, it means that the applied force has to be larger than the maximum static friction. And that means we're going to overcome the maximum static friction, and that means that our mass will start to move. If this combination comes out to be negative, that means that we have more than enough static friction available to keep the applied force from moving us. And so there will be no motion, which means that the acceleration in the system will equal 0. And the static friction will have to equal the applied force. Okay, so we'll talk about what that means here in just a moment. And then if you let's say in a very rare case, we ended up with a perfect balance here, where the applied force is equal to the maximum static friction. So in this case, we would also have no motion. The acceleration would be 0, and the static friction would have to equal the maximum. But this is kind of a dangerous game to play here, because this means that you're literally on the brink of motion. All you'd have to do is just maybe just give it a tiny little tap with your finger, and that would be enough to get that mass to start moving, because it wouldn't take much to overcome that maximum static friction force. But of these three case scenarios, which one are we dealing with? Well, let's find out. Here comes the test. We had an applied force of 20 newtons. We had an applied force of 20 newtons. We're going to subtract the maximum static friction, which was 36.8. And so that's going to equal a negative outcome. Again, I'm not interested in the numerical value. I mean, technically this would be a negative 16.8. But we don't want to make the mistake of saying that that's the net force, because that would mean that the block would have to start accelerating in the negative direction, and that is not how friction works. Friction is not going to help you move. Friction always opposes the direction of motion. So again, the important part is the sign. We ended up with a negative here. And that means that we're not going to move. So the acceleration is 0, and the static friction has to equal the applied force. This is what I mean when I say that static friction only uses what it needs. This system can provide us with up to 36.8 newtons of static friction, but how much static friction do we need to remain static? And the answer to that is pretty straightforward now. How do I keep this system immobile? Well, I would have to have a static friction force in the amount of 20 newtons. And that's what we get for this system. So we have our answer. Does it move? The answer is no. And since it's not moving, what is the static friction force? It's equal to the applied force. Okay, well, let's change things up a little bit. Let's increase the applied force to 50 newtons. So now what's going to happen? Well, again, we're going to ask the question, does it move? And we have our 3 case scenarios to consider. The only thing that I've changed in this problem is the amount of applied force. The coefficients are the same as what they were, the mass is the same, the layout of the forces are the same. As such, there is no change to the setup of the sum of forces that we're using. We're still going to test the maximum static friction to see if this block is going to move or not, but the normal force is the same as what it was. And so that means our expression for the maximum static friction force is the same. We plug in our normal force. There's the same expression. These are all the same numbers. So we have the same maximum static friction force that we had before. So there's no work that we have to do. We don't have to reproduce anything. It's already there. We just need to come back up here and, oops, I had my eraser on. All we have to do is come back up here and apply that test again. So now the test says we have an applied force of 50 newtons versus a maximum static friction of 36.8. Again, I'm not interested in the exact numerical outcome so much as I am about the sign on that outcome. This results in a positive, which means that I have more than enough applied force to overcome all of the static friction force in the system. And so this block will move. Because it's going to move, the acceleration is not going to equal 0. And because we're moving, we will have to apply kinetic friction to the system. We started with static friction, but then our applied force was more than enough to overcome that. So our block does start to move. It starts to move to the right. And once it starts moving, we need to switch over to kinetic friction. So the test is over. We have answered the question, does it move? Yes, it does. So now we continue with the physics, and the next question that we're going to ask is, now that we know this block moves, how fast will it move? So how fast will this block start to accelerate? I'm going to bring this equation over here so that we can see all of the values as we go to plug them in. We've been using the static friction force for most of this problem, but now we have to switch over to the kinetic friction force. Well, the only difference between that maximum static friction that we've been testing and the kinetic friction force is the coefficient that was used. We still have the same normal force. Granted, this block is going to start sliding across the floor, but it's still in contact with the surface. The block is still pressing its weight down on the table. The table is still pushing back with the normal force. We still have the same normal force. It's mg. So now we'll plug in our kinetic coefficient, which is 0.5. We have 9.8 times 0.5 times 5. And I am getting 24.5 newtons. That is our kinetic friction force. That is going to be placed into our equation up here. We had an applied force of 50 newtons. We had a kinetic friction value of 24.5. And that has to tell us how our mass accelerates. So we put all that together, 50 minus 24.5, that's 26.5 equals ma. The mass of the block is 5 kilograms, so we'll divide each side by the 5 kilograms. Oops, 1 second here. Got to reload my calculator app. I'm sorry, this is, that's not 26, that's 25.5. That's bad arithmetic on my part, sorry. 25.5, and then we divide that by the mass of our block, 5.1 meters per second squared. So now that the block is moving, now that we've overcome the static friction, the block is going to start accelerating to the right. With that acceleration, if we assume that the block started from rest, hence the static case, then we could say that the initial velocity was 0. We have an acceleration of 5.1 meters per second squared. So all we would have to do now is we would have to bring in a third piece of information so that we could do some kinematics. So maybe after sliding 2 meters, how fast is that block moving? Or we could ask, how long is it going to take to slide those 2 meters? And now we can answer that, because now we know how this block is going to be accelerating. One final thing that I will touch on here, the fact that we have our coefficients with this relationship tells us that the kinetic friction force will have to be less than whatever static friction force we encounter. Because remember, we always have to overcome the maximum static friction before we can start using kinetic friction. And so that means that for any system that involves motion, you're always having to overcome the maximum static friction, and so that means your static friction is the maximum static friction. This explains why you get better gas mileage on the interstate versus in town. Because when you're driving in town, what are you constantly doing? Well, you're constantly stopping at stop signs, you're constantly stopping at traffic lights, you're constantly stopping so that you can turn to go on another road. And because of that stop, go, stop, go, stop, go motion, you're constantly having to overcome the maximum static friction force between the tires and the road. And that increase in applied force to overcome that maximum static friction force is going to require more energy. And that energy is going to come from, ultimately, your gas tank. And so all that stop-go motion is going to result in you using more gas, as opposed to bringing yourself up to speed on the interstate and then maintaining that speed. A similar analogy is, remember we said you were going to try and push that very, very heavy box across the floor. So you push and push and push, and finally you overcome that static friction. The box starts to slide, and you find that it's actually easier to keep the box in motion and to keep the box sliding than it is to push it a little bit and stop, push it a little bit and stop. Because every time you allow the box to stop, if you want to get it in motion again, you have to apply a larger amount of force to overcome that static friction. So if you're ever going to be moving something, get it in motion, and then don't stop until you've got it where you want it. Otherwise, you're going to wear yourself out with all that stop go motion. All right, so that's going to bring us to the end of this video. I probably went over the hour mark, but that's okay because we got through everything that I wanted to discuss in terms of friction, defining the two types of friction. We have our fun equations here that tell us how we're going to measure our friction forces, and then we have the distinction between regular static friction that only uses what it needs versus the maximum static friction that we use as kind of a test to see if an object is going to move or not. So in the next video, we'll devote all of our time to more example problems using friction. We need to consider having masses on inclined planes. We need to consider maybe incorporating some tension forces just for variety in the problems. But a couple of example problems with friction in the next video, and then we'll put everything together in terms of all the forces that we've got so far, and then we'll see how some of these forces can cause circular motion to occur. So, see you at the next video.